Hi everyone. Java 16 adds records and pattern matching for instance of as standard language features, with sealed classes continuing to be a preview feature. In this screencast, I will limit the coverage of Java 16 to its language features, why you need them, and how you can start using them in IntelliJ IDEA. Let me start with records, which also happens to be one of the most popular features. Records introduce a new type declaration that simplifies the task of modeling your immutable data. Though it helps to cut down on boilerplate code significantly, that is not the primary reason for its introduction. Before the introduction of records, you would wrap your immutable data in a class, say person, and declare its fields, constructors, accessor methods, and other methods from class object like hashcode, equals, and toString. With records, you declare its components and that is all you need. Let's work with an example. To create a new record, access the navigation bar, select the package and invoke the new Java class dialog box. Type in the name, say order, and select the type as record. Hit enter and declare its components, say order ID, local date, and amount. And you're done. This is the minimum you need to create a record. Before we move further, let's quickly check the configuration of IntelliJ IDEA on your system. In this screencast, I'm using IntelliJ IDEA 2021.1 beta version. The production release will be out very soon. You can visit this website to find out what's new in 2021.1 and also download it. Let's configure 2021.1 to use Java 16 by selecting 16 as the project SDK and by choosing 16 preview seal types in the project language level for your project and module settings. You can also download and configure JDK from IntelliJ IDEA. In platform settings, click on SDKs, then click the plus sign at the top. Choose download JDK and select the vendor and version and the directory to download the JDK to. All the features that I cover in the screencast are also covered in this blog. The compilation process creates a full-blown class. A record is defined as a final class extending the java.lang record class from the core Java API. For each of the components of the record order, the compiler defines a final instance variable, order ID, local date, and amount. The methods toString, hashcode, and equals are also generated automatically for records. Interestingly, the name of the getter methods is the same as that of the data variable. It doesn't start with get or is. And since a record is supposed to be immutable, no setter methods are defined. But why would you want to use a record? Imagine you want to persist the details of, say, a person with a name and an age, using methods write to file and read from file. Basic methods, no fancy code here. Let's define this class as a regular class by invoking context actions and selecting create class person. Let me modify the name of the method parameters to this constructor as name and age. I also need fields that correspond to these method parameters. Let's create field for parameter age and name. The fields are already private. Let's mark them as final too. Time to generate accessor methods for the fields name and age. Let's also generate methods from the object class like equals and hashcode so that person's instances can work with collection objects. Also, the toString method to get a more readable form for person instances. Since I want to persist person instance to a file, let me make it implement the serializable interface. Now, let me run this class to see if we can store a person instance to a file and read it too. The output shows it works okay. Now, let me delete the class person and create it as a record person. Let me rename the components as name and age and make it implement the serializable interface because I want to persist it to a file. This is all you need. The compilation process generates the constructor, getters, hash code, equals, and the toString method. Let's navigate to the read-write object class and check if it can write this record to a file and read it too. Yes, it does. So by using records, you get all the functionality with minimal code. Can you modify a record? Let's see. Since the state of a record is defined using components in its declaration, it doesn't make much sense to allow the addition of instance variables or fields to a record. However, you can add static variables, say instance CTR, and instance or static methods to a record, say getInstanceCTR and getName in uppercase. The default constructor of a record initializes its state using the values you pass to it. But you can modify it to say validate the component values just like a constructor for a regular class. And do you know you can add a compact, canonical, or custom constructor to a record? If that sounds too loaded, let me show you how. Invoke the generate popup using Alt and Insert or Command N and select a compact constructor. Wow, it doesn't even have a parameter list, not even parentheses. For a canonical constructor, its parameter list matches with the list of components you defined for a record. And with a custom constructor, you can choose the components. Let's define a compact constructor to add validation code without adding the full boilerplate code. We can add the same functionality using a canonical constructor. You can even convert a canonical constructor to a compact constructor by invoking context-aware actions. Records are truly immutable. You cannot change their component values using reflection. And if you haven't tried it out yet, you can change the value of immutable strings using reflection. Let's work with the regular class and a record to show this. This is the regular class notebook, which defines a private final field page count. And this is a record point. Class useReflection defines methods change final field values for non-records, which instantiates notebook, a regular class, accesses its field page count, which is defined as private and final in class notebook. It then tries to modify page count value for the instance notebook. The other method in this class, change final for record, defines similar steps for the record point. It instantiates point, accesses its private component X, and tries to modify it. Let's run this class and check the output. As you can see, it could change the private final fields of a regular class, but not for records. You can define records with generics. Here is an example of a record called parcel, which can store any object as its contents and capture the parcel's dimensions and weight. And this is how you can instantiate this record. If you are working with records but need to transition it to the codebase of an older Java version that doesn't support records, you can quickly convert a record to a regular class by using the context action convert record to class. Or vice versa by using the context action convert to a record. Can you declare a record as one of the components of another record? Let's see. Record automobile declares its components as engine, another record, purpose, which is an enum, accelerate, an interface, int, which is a primitive type, and string, which is a class. You can add an appropriate annotation to the components of a record. Say, not null like this. You can also use third-party libraries like Jackson to persist records. However, the details might change over its versions. For example, for Jackson version 2.11.3, annotate your record components using JSON property. Let's execute this class to check if Jackson lets you persist records. Yes, it looks all good. For versions like 2.12.2 or later, this annotation is not required. Modify the Jackson version in my pom.xml, load the changes. Let me remove this annotation and execute the class to check if all is good. As you can see, yes it is. You can write records to streams and read them like other class instances. In this example, record person implements a relevant interface like serializable. And this class can write a person instance to a text file and read it using the I/O API in Java. You can refactor a record and modify the order of its components or types, modify their names, and add new or remove existing ones. This is how record person is instantiated now. Let me modify the order of components for record person. These changes reflect in the canonical constructor and also how its instance is created. You can also declare local records. Let's see why and how using an example. Class using records in Java 16 defines a record stock. Method getTopPerformingStocks defines a local record top stock. It makes this code easy to read and understand. This line of code gets a stream of stock instances. For a stock instance, create a top stock record with its components as the stock and its value for a given date time, returned by the method getStockValue. Sort all top stock instances on their value in descending order. Get the top two performing top stock values. Now, given a top stock record, extract the name of the stock. At the end, collect stock names as a list. Not just local records, you can also declare local enums and interfaces to encapsulate your data or business logic, but they cannot capture any context variable. For the local enum data, the enum constants foo and bar cannot be created using the method parameter input in the method test. Record is a restricted identifier, not a keyword, so you can use it to define variables or methods. But I would recommend you not to do it. It might look confusing to other developers. Now let's talk about the next language feature. As the name suggests, this feature applies pattern matching to the instance of operator. It offers a concise and safe way to extract values from an instance. Let's work with an example. We often use the instance of operator to check whether an instance is of a certain type, say string in this case. Explicitly cast this instance to string and assign it to another variable. Then use this variable to access members that are specific to the class string. There is an obvious repetition here. Let's introduce a pattern variable by invoking context actions and selecting replace with pattern variable. If the instance of condition is true, this pattern variable binds to the instance being compared, so we don't need additional variable declaration or explicit casting. The scope of the pattern variable is limited to the if statement. If you try to access it in the else part, it will not compile. However, it is not uncommon for developers to define fields using the same name. In this case, str value in the if part refers to the pattern variable and in the else part refers to the field. It is also interesting to note that if you negate the condition here, what happens to these variables? Now, str value in the if part refers to the field and in the else part refers to the pattern variable. Also, with Java 16, pattern variables are no longer implicitly final, which implies you can change their values. If you want to make them final, you can add the modifier final to their declaration. If I do that here, this code won't compile since I'm trying to modify the value of a final variable. Let me delete this line. It is a compile time error if the type of the method parameter here is string and you try to test whether obj is an instance of type object. Since object is superclass for string, this test will always be true and doesn't make much sense. The simplicity of pattern matching for instance of can be deceptive. Here is an example of how developers usually override the equals method for a class. In this case, monitor with two fields, model of type string and price of type double. Let's introduce a pattern variable. Now, merge the nested if statements and simplify the if statement. And this is how we can make the code concise and easy to read without repetitions. The magic happens when you get to know about the possibilities after using pattern matching for instance of in your code. For this example, let's start with introducing a pattern variable. Now, let's merge the nested if statements. The third step would be to replace loop with collection.removeIf. And lastly, to inline the variable list. Again, this is how you can make the code concise and easy to read without repetitions. If you don't need the pattern variables, you can inline them using the inline pattern variable refactoring. The shortcut is Ctrl-Alt-N on Windows and Linux systems and Option-Command-N on Mac OS. After you do so, all its usages would be replaced with explicit casting. If you extract a variable from a cast expression, IntelliJ IDEA detects that there were instances of checks made before. Then instead of creating a new local variable, it just converts the instance of to the pattern. Now let's talk about the last language feature that I want to cover in this screencast. The language syntax of sealed types enables you to restrict the classes or interfaces that can extend or implement them. The goal of this language feature is to let you define the possible hierarchies in your business domain in a declarative manner. But why would you ever need to create restricted hierarchies? Let's work with an example. Imagine you are creating an application that helps users with gardening activities. Depending on the type of a plant, a gardener might need to do different activities. Here is the plant hierarchy that we need for this application. And this is one of the ways in which a gardener might use this hierarchy. The problem code is the assumption you might have to deal with in the last else construct, defining actions even though you know that all possible types of the method parameters plant have been addressed. Though it might look unreachable now, what happens if another developer adds a class to this hierarchy? Sealed classes can impose this restriction on the hierarchies at the language level. Before I seal class plant, let me access its hierarchy by using Ctrl-H. Class plant has three direct subclasses: shrub, climber, and herb. Climber has another subclass, which is cucumber. Now, let's seal the class plant by using the context action seal class. This adds the contextual keyword sealed to it. A sealed class uses another contextual keyword permits to list the classes that can extend it directly. Its subclasses can either be final, non-sealed, or sealed. By default, IntelliJ IDEA declares all the subclasses as non-sealed. Now let me navigate to class herb and define it as a final class. Let's let shrub be a non-sealed class. Now, let's declare climber as sealed. When we do that, we need to follow the same rules as class plant. Cucumber is listed in the permits clause and is defined final. With the sealed hierarchy, you cannot create another class, say aquatic plant, that tries to extend the sealed class plant without adding it to the permits clause. This is a compilation error. Congratulations, you just decoupled accessibility and extensibility. Let's revisit the gardener class. After ceiling class plant, this code won't execute. However, with the current syntax of the if-else construct, you would need to define the else part. Who knows, this may change in a future Java version. Type test patterns might be added to the switch expressions in a future Java version. And with the enhanced switch expressions, you might be able to work with an exhaustive list of extended types. Sealed classes and their implementations cannot span across multiple Java modules. If a sealed base class is declared in a named Java module, all its implementations must be defined in the same module. However, they can appear in different packages. And for a sealed class declared in an unnamed Java module, all its implementations must be defined in the same package. As I demonstrated in the examples in this screencast, the classes that extend a sealed class must either be final, non-sealed, or sealed. A final class prohibits further extension. A non-sealed class allows other classes to extend it. And a sealed subclass must follow the same set of rules as the parent base class. It could be extended by an explicit list of other classes. A sealed class can be abstract too. Here is the modified code for class plant, which defines an abstract method grow. The extended classes could be defined as abstract or concrete classes. If you define a sealed class and its derived classes in the same source file, you can omit the contextual keyword permits and the name of the derived classes that are included in the declaration of a sealed class. In this case, the compiler can infer the hierarchy. Unlike the classes, interfaces cannot define constructors. Before the introduction of sealed classes, a public class could define a private or package private constructor to limit its extensibility, but interfaces cannot do that. A sealed interface allows you to explicitly specify the interfaces that can extend it and the classes that can implement it. It follows the rules similar to sealed classes. However, since you cannot declare an interface using the modifier final, because doing so would clash with its purpose, as interfaces are meant to be implemented, an inheriting interface can be declared using either sealed or non-sealed modifiers. The permits clause of an interface declaration lists the classes that can directly implement a sealed interface and interfaces that can extend it. An implementing class can either be final, sealed, or non-sealed. Soon, you might see the addition of sealed classes and interfaces to the core Java API too. Check out the API node for the interface constant.desc from the package java.lang.constant. Also, class java.lang.class adds two methods, getPermitted_subclasses and isSealed, for working with the sealed types. You can also use them to enumerate the complete sealed hierarchy at runtime, which can be useful. With sealed classes and interfaces, you can have an explicit list of inheritors that are known to the compiler, IDE, and the runtime via reflection. This closed list of subclasses makes the code analysis more powerful. For example, this is a completely sealed hierarchy of writing device, which doesn't have any non-sealed subtypes. Now, instance of and cast can check the complete hierarchy statically. Code on line 1 and line 2 are compilation errors. The compiler checks all the inheritors from the permits list and finds that no one of them implements the erasable or the char sequence interface. IntelliJ IDEA is not only committed to supporting new Java features, but also ensuring that our existing intentions and inspections work with them. IntelliJ IDEA 2021.1 supports all the new language features from Java 16. Try out sealed classes and interfaces, records, and pattern matching for instance of today. And we love to hear from our users. Don't forget to submit your feedback regarding the support for these features in IntelliJ IDEA. Thanks for watching.